So last time we saw this thing that the vector field f is conservative if and only if, I'll just abbreviate that IFF, you have path independence. Path independent. Well, we haven't written a complete sentence here, but that's covering the gist of it. And now, what if we have something more than just conservative? So what if vector field f is conservative, and in addition to that, C is a closed curve? Then what? Well, first of all, you need to say, well, what the heck is a closed curve? Yeah, so we better define that. Here's a definition. C is a closed curve if the terminal point coincides with the initial point. So, it just coincides, maybe is a fancy word, but it just means that the terminal point and the initial point are the same point. So the starting point and the ending point are the same point. So let's just draw some examples. So as an example, let's say you have a curve, capital C, that starts at this point drawn here, and it travels like this, and it reaches right back right where it started, maybe travels counterclockwise. That's an example. If you have, say, a curve C that starts here and goes around like this to me looks a lot like maybe just what happens normally with the unit circle based on its counterclockwise parameterization. There's another example. Here's another example. Let's say you start at the origin and you travel in a straight line to the northeast, and then you travel around in part of a circle, and then you travel along a straight line again. So you travel like this. I guess this is Pac-Man, right? But the outline of Pac-Man, if you just travel this way, travel along, this is another example of a closed curve. Let's also talk then about non-examples. So whenever you see a definition, I think it's important to think about examples and think about non-examples to really clarify what the definition is trying to say. So here's a non-example. Let's say you start at this point, you travel along like this, then you end up right here at the end. So you did not end where you started. So this is a curve. It's just not a closed curve. Here's another example. Let's say you start here, go around, but you don't quite finish that circle. This is a curve that's not a closed curve. And then you could also do maybe something like this. So start at this point, and at this point you're traveling this way, but you did not end where you started, so it's not a closed curve. Okay, so let's go back. Let's then, now that we've taken a moment to define a closed curve, looked at examples and non-examples, let's go back to the question that was asked here. Right? So suppose that we're in the situation that f is conservative and C is a closed curve. So certainly not one of these non-example ones. Perhaps one of the three examples we've already looked at. Then what? Then the integral of over the curve C of the vector field f, which we are saying right now is a conservative vector field. Okay. Dot dr. This is equal to, well, first of all, let's just write what it's equal to. So little f of r of b minus little f of r arrow of a. So we're applying here, the reason this equals is valid is the fundamental theorem of line integrals, which you can only use, this is okay, because the vector field f is conservative. Otherwise, you cannot apply this theorem. And then here's the real deal is it's important to notice that actually we're going to get the number 0 here. Why do we get the number 0? It's because C is closed. C is closed, so R arrow of B is actually the same location as R arrow of A. Right? So what I'm saying is you actually have right there and there the same thing twice. So f of a thing minus f of the same thing means you just have a number minus itself. And so you end up with 0. So theorem 3, let's just maybe not worry about numbering it, but there's a theorem. If you have a vector field, and this is conservative, aka path independence holds. We're being a little informal here about this. And C is a closed curve. Then the integral over that closed curve of the conservative vector field dot dr with an arrow is always equal to the scalar 0. Okay, the proof of this theorem is actually right there. It's the argument that we just gave right above. So let's take a look at an example. So question, let capital F of x comma y be the following vector field, angle bracket 3y, comma, angle bracket 3x. I'd like to find the line integral over the curve C1 of f dot dr and find the line integral over the curve C2 of f dot dr. Where, well, curve 1 is going to be the following curve. So we start at, there's the x-axis, y-axis. We start at the point 1, 1. Then you go 1 unit to the east. Then you go 1 unit north. Then you go 1 unit to the east. Then you go 1 unit south. Then you go 1 unit to the east. Let's get a little more parameterization arrows in here. And then you go 1 unit north. I believe you end up at 4, 2 when you do this. So this curve is C1. It's very, it's like if you have to drive in a city that's in a block system. Okay, and then the second curve, we'll also draw a picture, xy. So you have the point here, 1, 1 again. I guess we'll have to draw it down here. The point 1, 1. And then you travel along a path that looks like this. You go up like this, then like that, like this, like that, like that, and then maybe like this, right? So you travel along. I guess it's the right season for this. This is a hand turkey. Do you remember doing this? You ever draw one of these in elementary school? You draw your hand, trace out your hand on a sheet of paper. Okay, so I know this curve sounds a little strange, but I think this question is going to work out real nice because of the following, right? So to answer this, okay, there's a part A and a part B, right? 2 line integrals that we need to do. So for part A, look, method 1, if you were to choose to do this, is to parameterize 1, 2, 3, 4, 5, 6. Parameterize 6 separate line segments and take the sum of 6 integrals. Could this be done? Yeah, sure. I mean, is it going to be work? Yeah, it's not impossible, but it's just a little tedious. So let's not do that. Method 2 is to actually note that since the vector field that we were given, 3y, 3x, since that vector field is conservative, wait, why is this conservative? Let's actually put a remark for this in parentheses. So look, take a look at f of x comma y is equal to, well, 3xy. Then with this, the gradient of lowercase f is capital F arrow. Yeah? Okay, so that's, if you start with 3xy and you gradient that, you'll get 3x, so you get 3y comma 3x. Okay, so since we have a conservative vector field capital F, then the integral over C1 of f dot dr is equal to, take the potential function that we have here, 3xy, and start with the final point, 4, 2, minus take the potential function and subtract the initial point 1, comma 1. So f of 4, comma 2, well, again, f is right, lowercase f is right here, 3 times x times y. So 3 times 4 times 2 minus 3 times 1 times 1. And won't bother simplifying that any further. But that was much faster than method 1. Part B, we have this second line integral over the curve C2. So method 1, the traditional method here, would be to parameterize this turkey that we've drawn here, right? Ha 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 ha, no. I don't know how we do that, right? Like, it's just, this shape is too wacky for that. Okay, so method 2, since f is conservative, all we do is same deal like right here, right? We just look at the integral over C2 of f dot dr, and what we need is the value of lowercase f at the ending point, which was 1, 1, and we need to subtract off the value of f at the starting point, which was also 1, 1. And we could go back to this function to compute the value, but maybe the key thing to note is you just have a thing minus itself, so you're going to end up with 0. And this is a slightly more long-winded answer. What we could have done is just use the theorem up here, and instead, as a second argument, just said integral c2 f dot dr without even writing this stuff. We should just get 0 due to the theorem. It's just, I thought writing this might just provide a nice kind of reminder or a more concrete reason, example of why the theorem works. So in fact, let's just call this a third method here. Method 3. Since f is conservative, and then let's add a little more text here actually to this. Let's say since f is conservative and C2 is a closed curve, we have this.